Okay, so we're going to talk about exponential functions. This is the definition of an exponential function. A here is a fixed positive number that's not 1. And so we call A the base. So this is A raised to an exponent. A is the base, X is the exponent. And so now we're going to look at some examples of exponential functions. So to graph an exponential function, we start by taking some points for x, and now we plug those into our function. So that 3 is going to go in for x, so we get 2 cubed is 8. F of 2 is 2 squared, which is 4. F of 1 is 2 to the 1. F of 0 is 2 to the 0, which is 1. F to the minus 1, 2 to the minus 1. So remember the exponent rules. If the exponent's negative, it moves to the bottom. It moves to the bottom and becomes positive, or it changes sign. So since it's negative here in the top, it's positive in the bottom. Same thing happens here. That moves to the denominator, and so the result's 1/4. And then finally, uh, 2 to the minus 3. That moves the negative, and the exponent moves it to the denominator, and 2 cubed is 8. So to graph this, I'm going to use this program. So I'm going to graph the points. So there's the point 0, 1, 1, 2, 2, 4, 3, 8, and then minus 1, 1/2, minus 2, 1/4, minus 3, 1/8. So I graph the points, and now I connect the dots, and this is what my function looks like. Okay. So these ordered pairs came out of that table. So we'll go back over here. And so this would be the ordered pair 3, 8. This is the ordered pair 2, 4. The ordered pair 1, 2. So these are the x's and the y's, remember. So there's the x, and these are the y's. 0, 1, minus 1, 1/2, minus 2, 1/4, and minus 3, 1/8. So those are the points that we drew in the other. We'll go back and look at it again before we go on. So there's the point 3, 8, 2, 4, 1, 2, 1, 0, or 0, 1, whoops, minus 1, 1/2, minus 2, 1/4, minus 3, 1/3, and it continues on in that fashion in both directions. Let's look at another example. Let's look at the function f of x equals 3 to the x. And we're going to use the same x values as before. 3, 2, 1, 0, minus 1, minus 2, minus 3. So this goes in for x, so we get 3 cubed is 27, 3 squared is 9, 3 to the 1 is 3, 3 to the 0 is 1, 3 to the minus 1 is 1/3, 3 to the minus 2 is 1/9, and 3 to the minus 3 is 1/27. Okay, so we get the ordered pairs 327, 29, 13, 01, -1, 1/3, -2, 1/9, and finally -3, 1/27. Okay, so let's graph these ordered pairs. So I am going to turn off the ones we did last time. Okay, so here's the point 0, 1, 1, 3, 2, 9. Now my graph doesn't go up high enough to get to 27, so we'll just skip that and go -1, 1/3, -2, 1/9, and -3, 1/27. So I can put that one on there. Okay, so there's my points from the T table that we had. And now I'm going to connect the dots. And there's my graph of 3 to the x. Okay, now, if you remember, here it says that x has to be positive and it can't be 1. So far, a has been larger than 1, 2, and 3. But a does not have to be integers, and it does not have to be bigger than 1. So our next example is going to be 1/2 to the x, which we might also write as 1/2 to the x. But we'll use this one for now. So we make our t-table, and it starts out the same way as the other two have done. Okay, so f of 3 means that I get 1/2 cubed. So 1/2 times 1/2 times 1/2 is 1/8. F squared is 1/2 squared, or 1/4. F to the 1 is 1/2. F to the 0, that the 1/2 to the 0 is 1. Okay, now 1/2 to the -1. So what happens, I can do several steps here. So 1 to the -1 doesn't change anything, but here we get 2 to the -1. So it's negative and in the denominator, so it's going to change and move to the numerator and become positive. This one, so 1/2 to the -2 is going to be positive 2 squared. And then f to the -3 is going to be 8. Okay, so I'm going to go back to my computer, or my thing here. I'm going to turn off the graph we did earlier and do the one we just did. So we have the point 0, 1. So you may have noticed that this point was on all the graphs. -1, 2, -2, 4, -3, 8, 1, 1/2, 2, 1/4, and 3, 1/8. Okay, then I connect the dots, and there's my function. Now, looking at this, you can see that our graph is always going to be positive. So if you look at, let's see, so as here, this is 1/2 raised to exponent. So we can imagine that as we multiply 1/2 by itself over and over again, we're always going to stay positive. So our y values are always bigger than 0 because we're not ever multiplying by 0 or any negative number. We're just multiplying by 1/2 over and over again. And then over here, as I go this way, our graph just gets bigger and bigger, and so there's no upper bound. That means that our range is positive numbers, and our domain, so I can put any number I want, positive or negative, into the x. So I'm looking at this one here. So I can put any number, positive or negative, into x when I'm looking at 1/2 to the x. So that means, let me see. I have a text box somewhere if I can find it. No. All right, well, I don't know where it went. I guess I'll just go back to using the pen. Okay, so our domain, let me get rid of that. Okay. So let's put all of our functions up there. So that is x to the 1/2 to the x. This is 3 to the x, and this is, let me just label it. This is, whoa. Okay, this is f of x equals 2 to the x. This one is f of x equals 3 to the x. And this one is 1/2 to the x. Okay, so they're all positive, so they're all up here above the x-axis, and they're all along, you know, everywhere. Every number on the horizontal axis gets used. So that means that my domain yeah. Is minus infinity to infinity. So remember, those are the x values. The range are the y values, and they are positive. Now notice that over here, this direction is getting closer and closer to 0. And for the x, 1/2 to the x, it's also getting closer and closer to 0. That gives us a horizontal asymptote of y equals 0, which I can graph. All right, so in conclusion, anytime we have a function of the form a to the x, where a is positive, a is called the base, a is positive and not equal to 1, then our domain is all real numbers. Our range is positive numbers, and we have a horizontal asymptote at y equals 0. All right, that's it for this one.